What you're looking at fits inside the boundary of your city. It contains more mass than our entire sun. And yet, if you could scoop out a single teaspoon of what it's made from, that teaspoon would weigh 1 billion tons. That is not a metaphor. That is a measured physical fact. And we still don't know what's at the center of it. Today, we're going inside that object, layer by layer, to understand exactly what kind of engineering the universe had to perform to make that density possible. This is Cosmos Reconstructed, and today's subject, the neutron star. This star is dying. You can't see it yet. From the surface, it burns, red-orange, a furnace 20 times the mass of our sun. Light traveling at 300,000 kilometers per second would take hours to circle its equator. It's massive. For millions of years, this star does exactly one thing. It burns. At its core, nuclear fusion converts hydrogen into helium, helium into carbon, carbon into oxygen, neon, silicon. Layer after layer of heavier elements building up inside the star like the rings of a tree, each ring burning hotter and faster than the last. And then it hits iron. Iron doesn't release energy when it fuses, it consumes it. And the instant that iron core forms, gravity, which has been losing this fight for millions of years, wins instantly. The outer layers of the star, millions of kilometers of plasma, each layer weighing more than the entire Earth, fall inward at 70,000 kilometers per second. That is 23% of the speed of light. A star wider than the distance from Earth to Saturn, compressed to a sphere roughly 20 kilometers across in less than 1 second. All of that mass, all of that gravity, contained in an object the size of a city. This is the compression that produces the density that doesn't make physical sense. And this is where the real engineering story begins. For millions of years, that star existed in a state of perfect balance. On one side, fusion pressure, the constant outward push of nuclear fire. On the other, gravity, a force so immense it would collapse the entire star in seconds if left unchecked. When fusion stops, that balance breaks in less than 1 second. What's left behind after that collapse is a neutron star, and the internal structure of a neutron star is where physics stops following rules you learned in school. There are 4 distinct layers inside this object, and each one is more extreme than the last. The outermost layer, the crust, is iron, but not iron you would recognize. The pressure here has crushed atoms so tightly that electrons are ripped free from their nuclei entirely, forming a sea of free electrons surrounding a rigid crystalline lattice of iron nuclei. The density at the surface alone is already 100 million tons per cubic centimeter. And this is just the surface. Deeper in, the pressure becomes so intense that electrons are forced directly into protons through a process called inverse beta decay. Protons and electrons merge, producing neutrons. The nuclei here become so neutron-rich that neutrons begin to drip out of the nucleus entirely. Free neutrons, drifting between the atomic structures. Physicists call this the neutron drip layer. It marks the point where normal atomic physics breaks down completely. And then, the most exotic layer of any known object in the observable universe, a region physicists call nuclear pasta, not as a metaphor, as a precise structural description of what happens to nuclear matter when it's compressed to 100 trillion times the density of water. At this density, nuclear matter stops behaving like individual particles. It starts behaving like a continuous fluid, shaped by the balance between nuclear surface tension and gravitational pressure. The universe, working with nothing but raw nuclear force and crushing gravity, builds atomic-scale architecture. Spherical clumps, long thin strands, flat-layered sheets. Nuclear pasta is, by current estimates, the strongest material in the observable universe. A single sheet of neutron star lasagna has a shear strength roughly 10 billion times greater than steel. And yet, despite all of that pressure, across all of those layers, the neutron star doesn't collapse further. Something stops it, and that something is one of the most counterintuitive forces in all of physics. Neutron degeneracy pressure. Under the laws of quantum mechanics, specifically the Pauli exclusion principle, no two neutrons can occupy the same quantum state simultaneously. It is not a force in the traditional sense. It is a constraint written into the mathematical structure of quantum mechanics itself. Neutrons refuse to share space. When gravitational pressure tries to compress them further, they push back. Not because of any energy source, not because of any reaction, simply because quantum mechanics does not permit them to overlap. This is the engineering that makes a neutron star possible. Gravity, the most powerful macroscopic force in the universe, held in check not by fire, not by chemical pressure, but by a quantum mechanical rule that governs the behavior of subatomic particles. The two most extreme regimes of physics, general relativity governing the star's gravity, quantum mechanics governing its interior, locked in a permanent standoff inside an object the size of a city. And there's one more engineering detail the universe built into this object. Some neutron stars, called pulsars, rotate 700 times per second. A 20-kilometer-wide object packed with more mass than the Sun, completing 700 full rotations every second. The surface of that star is moving at a significant fraction of the speed of light. The magnetic field it generates is 1 trillion times stronger than Earth's. We detect pulsars as the most precise natural clocks in the universe, more accurate than any atomic clock humans have ever built. Because the rotation of a neutron star is governed by physics with no atmosphere, no friction, and nothing to slow it down. The universe built a perfect clock out of a stellar catastrophe. What the universe engineered here, in less than 1 second of stellar collapse, is an object that simultaneously demonstrates almost every known branch of physics. General relativity governs its gravity. Quantum chromodynamics governs its core. Nuclear physics explains its pasta layers. Quantum mechanics prevents its final collapse. Special relativity explains the behavior of its surface. All of it, compressed into an object you could drive across in 15 minutes. A teaspoon of it weighs 1 billion tons, not because the universe is being dramatic, because this is what matter looks like when gravity has had its way with it. And physics has drawn the one line it absolutely refuses to let gravity cross. Neutron degeneracy pressure, the quantum mechanical rule that says, this far, no further. Next week, we go inside the object that forms when a neutron star can't hold on, when gravity is so strong that quantum mechanics doesn't have an answer, the event horizon of a stellar mass black hole, and what the engineering of space-time looks like at the point of no return. If the engineering of the universe is something you want to understand, not just the what, but the how, subscribe. New breakdown every Monday and Friday on Cosmos Reconstructed.